So what I'm thinking for this part of class is we're trying to figure out which electric force equation to use when. And to help us out, I'm going to have us rewind to gravity, just like we did yesterday when we talked about gravitational fields, do electric field. We're going to go talk about gravity force to do electric force. So I'm going to break my paper up into like 6 sections in my head. Let's start on the gravity one. Remember there were 2 equations for gravity. One we started the year with, which was like nice and easy to work with. And one that we ended with like Coulomb's law, or sorry, not Coulomb's law, but the universal law of gravitation between 2 masses. How do we tell these apart? Well, the difference is actually the same picture, but in different sizes. When I can use this equation, Fg equals mg, I can use that for wherever the gravitational field is uniform. So the picture I have in my head when I use this equation is having the ground with a nice uniform gravitational field. The gravitational field points straight down, and anywhere in that uniform gravitational field, what does G equal to? Yeah. Because it's a nice uniform field, everywhere in this field, G is equal to 9.8. So I can use that equation wherever the field is uniform. And furthermore, field being uniform means all objects in that field have the same field value. I want to use this for things near the surface of the Earth. So this could be a person standing on the surface of the Earth. A mass in that field gets a force. So when do I use the other equation? Well, we used the universal law of gravity when I had 2 masses that created a non-uniform field. And even though we didn't draw this, imagine we had a field of 2 masses some distance apart. Their gravitational field lines would connect to each other. They would attract to each other. We would have equal and opposite forces. And the field wouldn't be uniform because it's these 2 bending towards each other. I want you to think that field would have the same shape as this one, attracting. So because the field is not uniform, I can't use the field equation. I'd have to use this for point masses. So let's go to the electrical equivalent of this. I'm going to have 2 electricity equations, and we'll be able to tell which one to use based on their picture. If it's a capacitor problem with nice uniform field, let's draw that. I like capacitor problems because it means like the field is nice and easy to work with. And just for funsies, I'll make that a field that points down, just so it really looks like the gravity picture we have right next to it. Okay. If that's my capacitor with its positive and negative plates, well then I get a field that points from positive to negative and is uniformly distributed. That means everywhere in that field, everything has a uniform field, and any object would have the same value of field. So I'm going to write this as Fe is equal to QE. I would use this for any uniform field. And because it's a uniform field, all objects have the same value of E. E is the electric field. Unlike G, where G is 9.8 though, our electric field could be any number. Imagine like I could charge the capacitor or I could charge the Van de Graaff generator to basically whatever I want it to be. So unlike before where G was always 9.8, E is just going to be some number that changes in the problem. Okay. I would still use the Coulomb's law equation though. I would use this for wherever I have any point charges. So if I wanted to get like, I don't know, an electron and a proton, a little atom here, their force would be attracted towards each other, equal and opposite, just like with gravity, attracted towards each other, equal and opposite. But I would use that for point charges. So if I put them side by side, electricity and gravity are kind of parallel to each other. You've got two equations, one for uniform fields, one for changing fields where you have like point charges or point masses. And just for funsies, because I said 6 things, right? Well, when we get 2 units from now, when we get to magnetism, we're going to do literally the same thing, except with magnetism, your magnetic force has a magnetic field B that acts on charged moving objects. So you'd have like a uniform magnetic field. Let's say my magnetic field points to the right. I'd have some sort of moving charge. And this would be a uniform magnetic field. And all objects would have the same B. In all 3 cases, fields create the forces. A gravitational field creates a force on a mass. An electric field creates a force on a charge. A magnetic field creates a force on a moving charge. So it's like we're going to do all of this again. We are going to skip the magnetic field like point current equations, because for that, there is an equation for it, but it's not one that comes up very often. Something like 2 currents over radius. So it looks really similar to the other ones, right? But we're not going to end up doing that last. So I figure, let me show you how to use this one, and then we will be on our way because that's our one new equation. I like started writing this here anyways. Okay, so let's say I have a field of 50,000 newtons per coulomb, and I'll do this as, maybe I'll make this like the lightning problem we looked at earlier. So let's say I have my lightning cloud, and it has its negative charges at the bottom. The ground has positive charges. So in between them, I've got this uniform field. Let's say that everywhere in the field, a particle experiences 500,000 newtons for every 1 coulomb of charge it has. So let's say I put in a charge over here, charge Q, and I'm going to give Q a value. Let's say Q is something like 5 microcoulombs. Since Q is only a fraction of a coulomb's worth of charge, it's going to experience some fraction of 50,000. So I'd write out my equation, Fe is equal to QE. I put in Q as 5 millicoulombs. E was 50,000. And the only thing I need to do before I put this into my calculator is make sure I convert. So I'm going to look milli up on my conversion factor chart. Milli is going to be times 10 to the negative 3 times 50,000. And this is something I might be able to do in my head. All right, 5 times 5 is 25. 10 to the negative 3 times 10 to the positive 4 is just times 10. This gives me 250 newtons of force. Now, this gives me the magnitude of the force. It's 250 is the size. What about the direction of force? If I put a positive charge right there, what direction is the force acting on it? Would the positive charge want to go up, down, left, right, go in a circle? right? So you would use this equation to figure out the magnitude of the number. Right? And then the direction is going to be, well, positives are attracted to negatives. So the direction of that force is up. That is it. That is how to use that equation. Some fancy things or things to note. I could be really mean here. Notice anything or anything I put in this field all has the same field value. All of these Q's that I drew, all of those Q's would have the same 50,000. But depending on the sign, that might be different. Notice a positive charge goes up because it was attracted to negative. But if I made this one negative, it would go down because it's attracted to the positive plate. So careful on the directions, follow your positives and negatives wherever they need to go. Right? And then the other trick is that everything in this field has the same value for field. You wouldn't have to like change it because it's up or down or left or right. Okay, so let us go try this.